And it's now where we can actually do some interesting things with the decomposition as it stands right now, which is start discussing the acceleration vector, or the second derivative of r of t. This is the acceleration vector. Along the curve. So we define the acceleration vector a of t to be the second derivative of the position vector which is the same thing as the first derivative of the normal velocity vector on the curve. But recall that we can decompose the velocity vector as the following, though the velocity vector is just the speed or the rate of change of arc length with respect to time multiplied by the unit tangent vector. Where both of these are functions of time. Remember that we showed from before that ds dt, rate of change of arc length with respect to the parameter t, is exactly the magnitude of the velocity vector. So this is just expressing that decomposition. And so, using what we know about the product rule, and this is actually even simpler to show than some of the things we talked about before with the dot product and cross product. This is going to obey the product rule, which means that this will be the second derivative of arc length with respect to the parameter t times this. I'll make the dot here a little bit smaller because this is not a dot product but just normal scalar multiplication times the unit tangent vector plus ds dt, or the velocity, rate of change of arc length with respect to the parameter t, multiplied by the derivative of the unit tangent vector with respect to t. This is the normal product rule. And if you remember the chain rule from before, this is the same thing as ds dt, and this derivative is the same thing as ds dt multiplied by the rate of change of the unit tangent vector with respect to arc length. So this is the same thing as ds dt squared times the magnitude of dt ds multiplied by dt ds over the magnitude of dt ds. Or, in shorthand, a good thing for you to check is to show that dt ds over the magnitude of dt ds is in fact the same thing as dt dt, so the derivative of the unit tangent vector with respect to time, or the parameter t, divided by the magnitude of dt hat dt, which is exactly equal to that unit normal vector that we defined before. This would be a good thing for you to go through and compute and check. Be a good, very good exercise. But what we've shown then is that the acceleration vector as a function of the parameter t is the same thing as the second derivative of arc length with respect to t times the unit tangent vector plus the magnitude of the derivative of the unit tangent vector with respect to arc length multiplied by the square of the first derivative of arc length with respect to time, or the parameter t, multiplied by the unit normal vector. And this is a very, very important decomposition. We can simplify this a little bit by defining a very special function. We can define the curvature of the curve r of t at point t to be the magnitude of the rate of change of the unit tangent vector with respect to arc length. And if we make this definition, then what we've shown essentially is that the acceleration along any curve, so we've shown that the acceleration vector decomposes as the second derivative of arc length with respect to the parameter t times the unit tangent vector plus the curvature, which could be a function of the parameter and in general is a function of the parameter t, times the square of the tangential velocity times the unit normal vector n. And this is a very, very important formula because it decomposes for any curve for us the what's called the tangential acceleration and the normal acceleration or centripetal acceleration for any motion, any curve at all. So specifically what we've shown, right, is this relationship right here, or if we simplify a little bit, we've shown that for any curve, any parametric curve, the acceleration along the curve is decomposed into two separate components. One separate component is the tangential acceleration, call it AT of t, and the other component is the normal component of acceleration, called AN of t. Where AT, the tangential component of acceleration, is exactly this first component, And the normal component of acceleration, or this is called the tangential acceleration, just saying that it's the second derivative of arc length. That's exactly what the that's exactly what the tangential acceleration is. And the normal acceleration is the curvature at a given point along the curve multiplied by the square of the tangential velocity multiplied by the normal unit normal vector. So this is called the normal or centripetal acceleration. And this is true for any curve for which these derivative manipulations are valid. So we'll say for smooth enough curves. And it's interesting that we can do this because we can actually use this physically when we're deriving the equations of motion, or when we're making certain physical simplifications about a given system. The main idea here is that we've shown that the acceleration vector can always be decomposed into a tangential component and a normal component in the direction of t and n respectively. We've also shown that this curvature function, it's a scalar function of the parameter value or of arc length along the curve. So the main thing that we've shown here is that curvature is a scalar function along the curve which measures the rate of change in orientation of the unit tangent vector per unit arc length along a given trajectory. Or in other words, maybe a little bit simply, or more simply put, it measures how curvy a trajectory is at a given point. So for instance, if we take maybe two comparison trajectories, where along one curve we have T1, and we'll call this point right here T2, the unit tangent vector for curve 1. And let's take a different curve maybe like this. We'll take 2 points on this curve. T1 hat, T2 hat. Well, if we're comparing curve 1 to curve 2, curve 1 has a low curvature, because there's a small change in the tangent vector, the unit tangent vector per unit length. But curve 2, on the other hand, has a high curvature. Because there's a large change in the unit tangent vector per unit length along the curve. So that's exactly what this measures when you calculate the magnitude of the rate of change of the unit tangent vector with respect to arc length. This is why we define curvature the way we do, and we've shown that the acceleration vector can be decomposed into a normal acceleration and a tangential acceleration. So let's go through and consider some basic examples, even more basic than the helix example. So suppose a particle moves with constant velocity. Well, mathematically this means that dv dt is equal to 0, and because dv dt is the same thing as the acceleration, this also means that the acceleration vector is equal to 0. So if you have a constant velocity vector, that means that your acceleration is 0. So let's consider a second example. Suppose a particle moves with not a constant velocity, but a constant speed. What is the acceleration along that curve? We can take our nice decomposition here. And we know that the acceleration will always be decomposed into a tangential component and a normal component. But if it moves at a constant speed, that means that the rate of change ds dt, or the magnitude of the velocity vector, is equal to constant. And I'll to denote that this is a velocity, I'll just call it vc, a constant velocity, or constant speed, not constant velocity. So if this is constant, that means that the acceleration vector is the same thing as the derivative. This is the second derivative of arc length, or the first derivative of ds dt, but ds dt is a constant. And the derivative of a constant is 0. So we have that the acceleration vector, when a particle moves with a constant speed, is just equal to the normal component of acceleration, or the centripetal acceleration, which is the curvature times the square of that constant velocity times the unit normal vector. So this is example 2, when a particle moves with constant speed. So even if a particle moves with constant speed, you actually still do have acceleration. You have purely centripetal acceleration. And we can actually use this to define the following. So this may seem a little bit confusing, but in reality it makes a lot of sense. So for instance, consider maybe a mass on a string, on a thread, that is being rotated from this origin right here, and this is our mass m, so radius r, and suppose we rotate this at a constant angular velocity omega, in which case the tangential speed of this mass is going to be, it's going to satisfy that the tangential speed Vc is constant, and it's equal to exactly omega times r. But the normal component of acceleration is kappa times Vc squared times n hat, which means that the normal component of acceleration is going to be kappa times omega squared times r squared times n. And there will be always a positive acceleration that points in this direction. But the tangential acceleration is 0, so the total acceleration here is just equal to this centripetal acceleration. Furthermore, we can actually show that the curvature of a circle, a good calculation to carry out, we'll show it for the helix and show that that reduces to the curvature of a circle. Curvature of a circle is going to be 1 over the radius. So kappa here is, for this motion, is 1 over r, which means that the acceleration for this sub-example is just going to be omega squared times r times n hat. And you get this nice formula for the centripetal acceleration, or the only acceleration experienced in such a motion. For our third example, we can consider the following. What happens if a particle moves along a trajectory with a constant direction vector t, or a constant tangent direction vector t? And if this is the case, then we can immediately say that the curvature is 0. Because the curvature is just the magnitude of the rate of change of the unit tangent vector with respect to arc length. And if this is constant, then this is equal to 0. So in which case the acceleration vector reduces to just the tangential acceleration vector, because the normal acceleration vector is 0. And because the curvature is 0, that means that the normal acceleration vector is 0. For a more direct proof of this, we can see this directly using the definitions. If t is constant, then the derivative of t with respect to the parameter t is 0, and we know that t hat is defined as the unit tangent, or the normal tangent vector divided by the magnitude of that normal tangent vector, which by that quotient rule is going to be equal to the derivative of v, or the acceleration vector, times the quotient, and then the denominator, minus v times the t derivative of v, of the magnitude of v, all divided by the magnitude of v squared. And algebraically this simplifies to 1 over the magnitude of v times a minus t hat, because v divided by the magnitude of v is just t hat, and this derivative of the magnitude of the velocity vector is just the second derivative of arc length with respect to the parameter t. And this is equal to 0. Remember that this expression right here is the same thing as the tangential component of acceleration. So what we've shown is that a minus the tangential component of acceleration is equal to the 0 vector, or this is just the normal component of acceleration is equal to the 0 vector. This is an alternative way of proving this. But what that means is essentially that we have that the curvature, right, is 0, and we have essentially rectilinear motion, so straight line motion. But that doesn't mean that the acceleration vector is 0. It just means, like we said before, the acceleration vector in this case is just equal to the tangential component of acceleration. So the acceleration just reduces to, in this case, only the tangential component of acceleration, which is the second derivative of arc length with respect to the parameter t multiplied by the unit tangent vector. This brings us to the final topic of today's lecture, which is a simplified formula for curvature. So recall that we define curvature as being the magnitude of the rate of change of the unit tangent vector with respect to arc length. The reason this is a simplified formula for curvature is because it's going to depend not on arc length but on any parameter. This expression right here is just dealing with the derivative with respect to arc length, but sometimes parameterizing with respect to arc length is tough if you just have a function or a vector valued function of a scalar variable defined in terms of some arbitrary parameter t. The first thing we can do is rewrite this as dt ds times dt hat dt. This is just the chain rule. And also from the implicit function theorem, dt ds is the same thing as 1 over ds dt, or 1 over the magnitude of v. So the curvature really is the same thing as the magnitude of the derivative of the unit tangent vector with respect to the parameter t divided by the magnitude of the velocity vector itself. Or to express this in a slightly different way, we have that the magnitude of dt hat dt is equal to the curvature k. Remember, this is a function of the parameter t in this case now, times the magnitude of the velocity vector, which is also a function of t. And remember how we decompose the acceleration vector. The acceleration vector was equal to the second derivative of arc length, or the first derivative of what d squared s dt squared times t hat. This is the tangential component to the acceleration plus the normal component to the acceleration, which was the curvature times ds dt squared times the unit normal vector n. And now if we consider the cross product of the velocity vector with a, remember that the velocity vector is the magnitude of itself times the unit tangent vector. We take the cross product of that with this acceleration vector. You get that this is equal to the magnitude of v times the second derivative of arc length times the cross product of t hat with t hat plus kappa times magnitude of v cubed times the cross product of t with n hat. And the cross product of any vector with itself is 0, so this is 0. And we can actually use this right here. We're going to define what's called b hat, or the binormal vector. To be exactly the cross product of t hat with n. And it's possible to prove directly that the b hat is both, well, judging from the fact that it's a cross product of t hat with n hat, b hat is perpendicular to both t hat and n hat. And another thing that we can prove, and I'll prove that right here, is that the length of b hat is equal to 1. The proof of that is very, very straightforward. The magnitude of or length of any cross product from chapter 6 is the length of the first vector times the length of the second vector times sine of the angle between them. And the angle between them is 90 degrees, or pi over 2. And because t hat is a unit vector, this is 1. N hat is a unit vector, so this is 1. And then sine of pi over 2 is sine of 90, or 1. So I've just proven to you that this binormal vector has a unit length of 1. This is a little bit of an aside from what we're trying to do, but trust me, we're going to get a simplified formula for curvature from this. So let me take you and just kind of show you that binormal formula, the binormal vector itself, on back to the helix example, because we want to see that this is in fact giving us exactly what we would expect. So the binormal vector is this blue vector right here. You see it's perpendicular to both the tangent vector and the normal vector. And at this point we've done it. We've successfully constructed our frame. This is sometimes called the Phrenae frame for reasons we'll get into later. But it's a 3D frame of 3 vectors that for any curve can be defined and follow along the curve tangentially, normally, and binormally. So let's see what this looks like for a second. And you see here plotted out the tangent vector, the normal vector, and I've now included this binormal vector b. And we can see that these 3 vectors do exactly what we set out to do at the very beginning, which was to create an orthonormal frame that travels around any given curve that we have with a tangent vector, a normal vector, and a binormal vector. So this is the so-called Phrenae frame, and we'll see why it's called that next lecture. But getting back to what we were doing before, which is that we now have a simplification. We've shown that the cross product of the velocity vector with the acceleration vector is in fact equal to the curvature times the velocity vector magnitude cubed times the unit vector b, or the binormal vector. And if we take the magnitude of each side of this equation, we have a very remarkable formula. So if we solve for the curvature, we have that the curvature is equal to the magnitude of the cross product of the velocity and the acceleration at any point divided by the cube of the velocity vector. And this is the simplified formula for curvature that I was talking about. It's simplified because now if we have a given parametric curve that's parameterized in some way, we can go through and directly calculate the curvature. So let's finish by going back to the first example, the helix, and we'll calculate the curvature for the helix. So recall the previous calculations that we've done for the helix. Namely, we've shown that the velocity vector is equal to this right here. This is what we found for the velocity vector of our helix, and we also calculated the magnitude of that velocity vector to be this right here. And so the last thing that we need to compute using this curvature formula will be the acceleration vector, which will be the derivative of the velocity vector, which is going to be negative omega squared r times cosine of omega t, negative omega squared r times sine of omega t, and then the derivative of a is just 0. And so you'll recall from chapter 6 that the cross product of v with a can be computed using a nice computation technique. We list out the components of the first vector, which are these components right here, and then we list out the components of our second vector, which is going to be and then we go through and calculate the determinant of this matrix using the normal determinant formula, but with the added assumption, right, that this I hat, j hat, and k hat are all the typical unit vectors. So sure enough, when we go through and do that, we're going to get that there's a pretty big simplification here. We'll have that we're going to choose to do an expansion in this row right here. So the resulting determinant will be I'll do this on the next line down. And it'll be minus this value right here times I hat and then k hat a. And then because of this nice 0 right here, right, the third component in this expansion, the determinant expansion, will just be 0 because of this 0 right here. So we have that V cross A will be equal to negative omega squared R cosine of omega t times A j hat, and minus this times this, that becomes plus omega r cosine of omega t k hat, and this becomes plus omega squared r sine of omega t multiplied by a I hat minus this times this, which is plus omega r sine of omega t times k hat. And if we kind of bring all these terms together, this becomes a times omega squared r sine of omega t times I hat minus a times omega squared r cosine of omega t j hat. Oops, sorry, I just realized I have a small little typo here. The velocity vector only has a negative first component. So this should be negative right here, or positive right here, not negative like I wrote when I wrote that down. So that would mean that then when we go through and calculate the determinant, it's this times this right here, where this is positive. And that's going to mean that this sign right here is actually a negative sign. Sorry for that mistake. But so then this becomes positive, or it's still negative right there. But what does become positive is this times this. So we have omega cubed times r, and then it'll be cosine squared theta, or cosine squared of omega t, plus omega squared r sine of omega t times this right here. So it'll actually be r squared sine squared of omega t times k hat, or it's exactly equal to a times omega squared r sine of omega t negative a omega squared times r cosine of omega t. And because this is equal to 1, the third component here is just omega cubed times r squared. And when we go through and to use the curvature formula, we need the magnitude of this. We're going to go through and simplify this to get the magnitude of V cross A is equal to the square root of this term squared plus this term squared plus this term squared. This squared plus this squared plus this squared. Which simplifies to, we get sine squared plus cosine squared here. This negative sign is inside the square, and that's going to give us a 1, which gives us a times omega squared times r squared plus omega cubed times r squared squared, which simplifies to a squared times omega to the 4th times r squared plus omega to the 6th times r to the 4th which is the same thing as omega squared times r times the square root of a squared plus omega squared times r squared. And so, lo and behold, after a relatively long computation, we've stumbled upon the fact that the curvature is equal to the magnitude of cross product of the velocity and acceleration before, divided by the magnitude of the velocity cubed, which now we know for the helix is omega squared r times a squared plus omega r squared to the 1/2 divided by the velocity cubed, and the velocity for the helix, remember, was a squared plus omega r squared to the 1/2. So if we cube that, it's the same thing as a squared plus omega r squared to the 3/2, and 1/2 minus 3/2 is -2/2, or -1. So we have that this is the same thing as omega squared times r over a squared plus omega times r squared, which is a remarkable formula because it proves that the curvature of a helix is constant, and it's gives us a very, very nice way for determining exactly what that curvature is. So if I give you a helix with a frequency omega, an a value of, say, like whatever the a value is, remember a is the growth rate along the z-axis, and r is the radius of the central circle of the helix, you can use this formula to directly determine the curvature of the helix. But what's more important here is seeing the process used to go through and derive this special formula that we started out with. So this formula right here, and then also apply it to a specific problem. By the way, a special case of the helix is the circle when a is 0. And when a is 0, this formula for curvature reduces to kappa being equal to omega squared times r divided by omega r squared, which is omega squared times r squared, or that 1 over r that we used earlier. So this is a very, very special example for a number of different reasons, but this is where we're going to conclude the lecture for today. Thank you very much for listening, and I hope you learned something. Take care and have a great day.